Okay, thank you for the introduction. I would like to thank the organizers for giving me the opportunity to present this work and also for putting together this nice workshop. So the overview or outline of this talk is the following. I will, as you might have seen on the previous picture, my background in recent years is slightly different. However, this work inspired us to go towards stochastic homogenization, and in order to understand the motivation, I will speak first very briefly about continuum solvation models that gives some motivation for the work that is presented afterwards, namely a new embedded corrector problem that we like to define. Then I will spend some time on give details on the numerical implementation and finish with some numerical results. So this is in collaboration with Eric Sanchez, Virginie Erlacher, and Frédéric Le Gol. Good. So as promised, we do a little deviation in the beginning. So we consider a molecule, and that is this solute molecule that is embedded in a solvent. And the solvent here is represented by some solvent molecules. And typically in a continuum solvation model, you say the solute is embedded in a hollow cavity omega, and the set of all solvent molecules is represented somehow by a macroscopic model, macroscopic average, that is a continuum medium with some dielectric constant epsilon s that somehow is the macroscopic model of the bulk water molecules here. And then, since these water molecules, they can polarize in the presence of a charge that is coming from the solute, so this emits electric field, they can polarize. And the ability to polarize is reflected in this dielectric constant epsilon s. Okay, and then in the framework of computation chemistry, for this reduced or simplified model, you want to be able to compute the electrostatic interaction between solute and the continuum solvent. So given a charge density rho in here, you want to compute the electrostatic interaction energy. And while in spirit of quantum mechanics, there are other kind of interactions which are dispersion or repulsion, so this is not modeled here. Okay, so the PDEs are rather simple. So first of all, if the solute density is given by rho, I consider by phi the free space potential. So this is the electrostatic potential in vacuum, so if no solvent is present. However, if you are now put everything or embed in a solvent, so in some macroscopic bath or environment, then the PD solves this kind of problem where we have now this epsilon s or epsilon function that is 1 equal void in the inside and epsilon s on the outside. So this is a elliptic interface problem that we like to solve. In practice, you do not want to solve exactly the V because you assume that whatever model you have for your solute already includes the electrostatic interaction. So what you actually want is the difference due to the solvent, so the field or the potential in the presence of the solvent minus the potential in vacuum, and only this type of energy or this contribution is added to the model because electrostatics is already included in the model of the solute. Okay, so far so good. So you can change your unknown to W. That's what you want to solve. This is the definition of the energy, and this is the corresponding PD for the W, where now you have a jump on epsilon times the normal derivative of this reaction field. So in the extreme case, when epsilon s is infinity, then actually this medium acts as a perfect conductor, and in a perfect conductor there is no field, electric field, so you can put the potential V equal to 0, and you don't have actually to solve on the outside. And this is exactly the so-called Cosmo model. And you have to solve a PD, which is actually only a Laplace equation in the inside that matches some given boundary condition. Okay, and due to the fact that indeed epsilon s is not equal to infinity, chemists introduced some kind of empirical scaling function that reasonably captures the trend. Okay, that's the model. Let me emphasize that the difficulty is not to solve such a problem in 3D. The difficulty is the geometry, so it can be thousands of atoms, and typically in the molecular dynamics simulation you have to do this at every time step. So maybe 1 million of times you have to solve this problem. So meshing is, for instance, not allowed. And we did introduce some domain decomposition strategy to solve this kind of problems by saying I solve local problems in each of the spheres, and since I have a very simple geometry, I have a sphere, I look at the harmonic field with some prescribed boundary condition, one can use the maximum spherical harmonics, because if you prescribe the spherical harmonics on the boundary of a sphere, the harmonic extension inside is given for free by a separation of variable argument. Okay, and then you can solve these local solvers and you can exchange boundary data from one to the other and solve this iteratively. So this results in a rather fast solver. So this is the state-of-the-art by York and Karplus. And so it's really a game changer, and the gradients what make it fast, that's what I want to emphasize here. These are the spherical geometries in combination with spherical harmonics. And also the fact that everything can at the end be formalized in terms of integral equation. Because this is, let's say in electrostatics you have the Green's function decays like 1 over r. So this decays very slowly, and integral equation are able to handle this scenario on computing on an unbounded domain. On the other hand, you could say, okay, I take a large enough domain, I put Dirichlet boundary conditions, homogeneous one, but then I need really to have a large domain because this 1 over r decodes very slowly. So this is the advantage of integral equation in this case, because you can tackle unbounded domains, which shall be important in the following. So the questions we were asking is, can we borrow this methodology for stochastic homogenization in the particular case when we have spherical inclusions? Because then it looks promising that we can use certain tools as spherical harmonics, because we have spherical geometries, integral equations, and so on in this framework. Okay, so let's come to the stochastic homogenization. So a typical target is maybe such kind of a prototypical example of material, why we have a biphasic material with ellipsoidal inclusions. In the following, I will assume only spherical inclusions, but our long-term goal is to extend this to ellipsoids at some point. Those size are typically epsilon, so much smaller than what you would like to resolve in practice. But you would like to know what are the macroscopic or effective homogenized properties of this material. Good. Let me introduce, for sake of fixing the notations, curly M be the set of symmetric matrices that are bounded below from 0 and positive and bounded above. Then for some small scale parameter, let A epsilon be a matrix valued functions with values in M, so that typically, as we have seen in the previous talk, you're interested in the solution of this problem. Okay, so A epsilon is typically in this case, now there's a scalar case, when U is a scalar, is a thermal diffusivity matrix of the material. And U epsilon can be interpreted as the temperature, for instance. Good. So in 2D, the scenario would look like this. In 3D, like this, many balls. So let me already do the comment on intersection of spheres. The whole methodology can be adapted to it. The numerical computation will, however, be more expensive, but it could possibly have intersecting spheres. As we have in the case of molecules, we have intersection of spheres. This case can be handled. Good. So there are different settings possible. So I'm not an expert, so I'm going to be quick on that. I leave that for others. So you can assume that the setting would be like that A epsilon is periodic, or quasi-periodic with small scale parameters epsilon, or where epsilon, A epsilon of x is a realization of a random stationary function, A stationary. And in a broad sense, stationarity means that the distribution of the inclusions at a certain point is statistically the same wherever you look in space. Okay, and then in these cases, and if A epsilon is bounded and bounded away from 0 uniformly in epsilon, then problem 1, the previous problem, admits a homogenized limit, and even there is a constant homogenized matrix A star, blah, 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 as we have seen in the previous talk. Okay. So, now the classical result is, while this is the case where we focus on the third case, where we have indeed a random variable, and then the constant matrix A star is determined by its action on any vector P in terms of this average here. Okay, where now this corrector can be characterized to be the solution of this PD. Okay, so the good news is that A star is constant and deterministic, even in the stochastic case. And we have a PD that gives us the solution for A star. However, this is on an unbounded problem. Okay, so once A star is known, then everything is fine, but to come to this problem, you have to solve a problem in the whole space. Okay, and in practice, the most prominent approach is to take the field here, the coefficients, take a large enough box and impose periodic boundary conditions, solve the corrector problem on this large box with periodic boundary condition, and then compute the homogenized matrix given by its action on P like this. Okay, so this is the standard approach. And then it is shown that this one is indeed converging as R goes to infinity to A star almost surely. And I should also mention there are optimal error estimates by Gloria and Otto. Okay, so this is, to my understanding, somehow the state of the art. Now here, we do a different ansatz. As I said, we assume that we have spherical inclusions with constant material coefficients. So we have piecewise constant material coefficients. And let BR be the ball of a radius R that is centered at the origin. Now, it's hardly seeable, but here is a ball, this ball of radius R. And what we do is we take this, we copy it here, but then we embed it in an infinite continuous media with some material that is characterized by a constant matrix A. Okay? So this ARA is, whenever X is in the ball, is the original field. Otherwise, we take an arbitrary symmetric positive matrix A to complement. Okay? That's the first ansatz and ingredient. Now you can, associated to this new field, define a corrector problem that is, for some direction P and some realization, and for some background coefficient A, you can find the solution to the PD where now this field here the original field was A, was replaced by only considering whatever is in the ball BR and otherwise extending with this matrix A. Okay, now the good point is here that A is constant on the outside. So now we're coming back to integral equations. If you state this form or this PD with integral equation, you can capture the whole space problem and you can even discretize it. So we're not necessarily forced to be that our computational domain is bounded. We can have a non-bounded computational domain. What is important is that for some radius r, the exterior of this ball needs to be constant, and then still you can discretize. So this corrector problem is somehow related to a Shelby's inclusion problem, although to my knowledge this is only the case where we have one inclusion inside and then the bigger ball. But here we have arbitrary many inclusions here in this larger ball BR. For sake of a simple notation, I omit the dependency on omega in the following. Okay, so let's think of a deterministic field, although it applies to random fields as well. No. Okay, let me do the change of variable. I think this is quite standard in the community. So instead of looking at growing balls and balls with more and more inclusions, we define the unit ball and we scale the medium to be smaller and smaller with always the same fixed size b, but we have smaller inclusions and they're also more numerous with increasing r, so to say, if the change here r is increasing. Okay, so then we restate this corrector problem in the following way. So let us assume the correct functional space. So for some direction p, for some a, that is some random field or deterministic field in this case, given, and some background coefficient a, we find the corrector that solves this PD, where now here this A is inside the uniball is the original A scaled by R times X and otherwise A. Okay, so we have this rescaled version which is equivalent to the previous one, but we're now fixing the sphere or the uniball to be the uniball and make the medium smaller. Okay, so you can ask, is this a smart way of doing it or not? We thought we're smart. So we tried it. So you can say, okay, I can solve this corrector problem. I can define an effective matrix following the standard arguments as the same formula as we have seen before. A0R applied to P is given by this kind of formula. Now the following lemma says the following. The sequence of A0R converges to the homogenized matrix A star as R goes to infinity only the case when A, the background, original background coefficient is equal to A star. So we thought we can choose some A and then have a homogenized coefficient that so that A0 star would converge to A star, but it turns out that from the beginning we need to impose A star in the background in order that this sequence of correctors converges to the right limit. So this is first of all not such a good.
Is this because you have mostly A star in the domain of A star itself, or the reason it's converged?
No, I give some explanations here. So first of all, this is counterintuitive because usually G convergence is indifferent with respect to the boundary conditions that you impose for Dirichlet boundary conditions. But embedding the corrector problem in an infinite domain with environment which has some characteristics A is much stronger than imposing directly boundary conditions. So you're preconditioning your solution too strongly with this infinite bath of the environment so that it converges to the wrong limit.
But most of the volume is A star, is that right? Or
Well, it depends whether you do the rescaling or not. It applies in both cases. It's just a different point of view. I mean, you can think in the case where you don't do the rescaling, you have larger and larger ball BR, and so you have more volume, and you take the average over this.
this
Yeah.
is stochastic.
This is in both. Yeah.
Almost sure.
Yes. Maybe it's not so smart at all. Let's see if we find a remedy. Okay, so the answer is the following. We have to include this A star somehow in the solution process, because the solution depends on it. So can we define somehow A self-consistently with the field A, in the sense that there should be a relation on whatever I compute here should already somehow be in A, so A should also be an unknown that you determine somehow on the fly. For a given R, you define not only the corrector but also the A. And then you make the limit as R goes to infinity, and you hopefully converge to the right limit, because this A is somehow self-consistent with this with the original field. To put a little bit of light on that, let us rewrite the original embedded corrector problem as the minimizer of an energy functional. So it is a PD, it's a cursive PD, so we can associate the energy functional such that the solution of the PDE is the minimizer of the energy functional. And this is the energy functional given by this. Okay, so if you take the Gatto derivative, then you find the PD. So now what I call calligraphic J of PA of A is nothing else than the evaluation of the energy associated to the PD for the minimizer. So this one here. So here's just rewritten. Now consider the mapping that goes from P to WP, to the corrector. So we have a linear PD. So this mapping is linear. Okay, so WP depends linearly on P. Now, if you put here the WP in this energy functional, then we have here, this is linear in P. So if you put WP instead of V, this is also linear in P, 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 linear in P. So this means actually that this functional is quadratic in P, the direction. So this energy functional is quadratic in the direction. So therefore, there exists a unique symmetric matrix that I call GA, such that for any direction, this JP is P transpose, this matrix times P. Okay? So we give an implicit definition of some matrix that must exist due to the fact that this function is quadratic in P. Okay. So now if you take the canonical basis EI, and you sum over all the directions from 1 to D, you sum up this kind of energy, then on one hand you see that this is the trace of GA. On the other hand, the mapping that associates to a background matrix A this energy functional that is now the sum over all canonical directions is indeed concave. Moreover, in 3 dimensions, this functional is strictly concave. Okay, that is an important result that we use in the following. So let's now try to give a first definition for a potential candidate A for the background material. So rewrite the corrector problem as A plus on the ball the perturbation of A minus A. Okay, so this can be seen as a local perturbation of the homogeneous background material A. Now, WP can be seen as the perturbation of an incident wave that has wave vector P that is induced by the local perturbation in B. So in some sense, or this is a zero frequency wave that has infinite long wave number, and this is, or let me see, minus Gp is the scattered energy with respect to the direction P. So you have this wave that going through the material, and you would like to choose the background material such that there is little scattering energy as possible. Okay, so for one direction, and if you sum up, then you have exactly this minus Ja, which is the sum over all directions. So this can be interpreted as the scattering energy of a wave that is infinite, has an infinitely long wavelength that is going through this perturbation, and you want the background material that minimizes this scattering energy. Okay, so this gives a definition, a first definition of some homogenized coefficient for a given R, namely that is the A matrix that is minimizing the scattering energy. And by the previous lemma, there is existence of this coefficient A1R, and even in 3D there is a unique A1R. Okay, so unfortunately but we don't have very convincing intuitive arguments why the second and the third definitions are good definitions. Well, if you nail down everything to 1D, you see that it is reasonable. However, there's no such a clear illustration like this scattering wave for the two remaining definitions. There will be two more definitions. So first of the second one is, now given this scattering energy for a certain given P, and you plug in the previous definition, we know that there is some GA that is giving this quadratic form, and this GA we call A2R. And thirdly, you could think there is this and this should be somehow the same. This should be the homogenized coefficient. So you can ask yourself, well, shouldn't there be some self-consistent definition where we look for A3R that satisfies the equation? Okay. So here's a summary. And so the lemma ensures existence of the first two and uniqueness in the 3D case. In the third case, we can ensure that if the homogenized field is a scalar, then we have existence of a fixed point of this mapping. Okay. Sorry? In this case, in the third, yeah. So then is the following convergence result. The sequences A1, A2, satisfying definition 1R, are converging to the homogenized matrix A star almost surely as R tends to infinity. If the third one exists, which is somehow left apart, then it also converges to A star almost surely. Okay, so this is the theory. Now, in the second part, I would also, to illustrate a little bit on the numerics, because this was somehow the main intuition of the whole thing to make something that is tractable, and we had some precise way of numerics in mind when we designed this problem. Okay? So let me explain you how you can derive integral equations for this kind of problems. So this is this typical corrector problem. So now in all the following we assume indeed that we have scalar quantities here and that we are in 3D. Okay, I will need some notation. So we have, I copy from here, this large ball BR. Then on the outside, this is omega infinity. And here we have these inclusions. And in such an inclusion, we have the coefficient AI. And I call this inside here omega I. Then we do have a normal outward pointing that is Ni. All the material that is not an inclusion but inside the ball is omega 0, and the normal, exterior normal to omega 0 is called N0. In the same way, you have here N infinity and you have N0. Okay? So this is the setting, and it's given like this. Okay? And gamma I is the boundary, of omega I. Good. So now, since the coefficients are piecewise constant, what you want to say here is nothing else that in each subdomain, your corrector is harmonic. It should be continuous across each of the interface, and there's some prescribed jump of 8 times the normal gradient across the interface, which is given by minus the jump of 8 times p. So the jump in my case is, for instance, if we have a gradient of w, then it is the gradient from, let's say, from omega I dot ni plus the gradient w from the omega 0 times n0. So I write it as a sum, but note that the normals, they do jump, they change signs, because ni is minus n0. So somehow this is standard notation in discontinuous Galerkin, but this has the advantage you don't need any convention. Okay? Okay, so now you have a function that is harmonic except on some interfaces. So this means it can be represented, referring to potential theory, by a single layer potential. That means WP can be written as an integral over all the interfaces of some density nu convoluted with the 1 over R kernel. And in principle, we know what this nu is. It is the jump of the normal derivative of WP. Unfortunately, this is not known. We only know the jump of 8 times gradient of WP. But we have a parameterization somehow of the harmonic function WP. Now, to derive the integral equation, start from the point where you assume to be given WP on all the interfaces. So, on the exterior ball, but also on the interior spheres here. Okay? So if you know this lambda I or WP on each gamma I, what you can do is, for instance, in a sphere here, you can solve for the harmonic extension inside. Okay? This is just a sphere. This can be done numerically quite efficient. Then you know your field inside perfectly. That means you can compute the normal derivative from the inside. So given here the Dirichlet trace, you can solve for the harmonic extension inside and compute the Neumann trace. That means you have you can cheaply compute the Dirichlet to Neumann map. Okay, so this means here, given lambda I, you can apply some local operator in order to get the Neumann trace. Now from the jump condition, this guy, we know that if I know the inside of the trace, I can compute the outside of the Neumann trace. So by rearranging these terms here, I can write the Neumann trace from the outside equal to that. And with this at hand, if we write the definition of this density that we would like to define, which is the jump of WP, that means the Neumann trace from the inside plus the outside, you replace the outside by this formula here. And again, this you trace back to lambda I, you can write this. Now, if you apply the single layer potential to this quantity nu, you find back the initial lambda I. So this closes the loop, means you have derived an equation. Okay, so this is the integral equation that we have stated before. So if lambda j is given, then finding this interior Neumann trace and so on can be done by this in order to get the nu. So this corresponds to this part here. And since P is data here, this goes then to the right-hand side here. You have to do this guy. So this is a... Now you can discretize that. That means lambda j you can write as a series of coefficient times spherical harmonics. Because now each interface is spherical, the large one or the small ones. So you can have some kind of a spectral approximation of your density on the interface in terms of development of spherical harmonics. And if you know the lambda j, because this is a local equation, you can immediately derive a function for the nu j here by just applying these few factors here. And then you can test this equation in the typical Galerkin framework. You take a test function, also spherical harmonics, and you test it on each of the spheres, and this gives you a linear set of equations that you would like to solve. Okay, so one remark is that now the mapping from lambda j to nu, this is indeed local. This Sj is a global operator, okay? So this means if I have a density on one sphere, then in order to compute Sg on the other one, it's a convolution over all the spheres, so there's a global interaction, and this can be handled with the fast multipole method. So if you write more precisely for nu, what is the potential at a point x, where we assume here that each of the spheres are centered at Rj and have radius little rj, then this is the value of the potential, where we have to sum, as you see, over all the different spheres. So you can rewrite this as a potential like this and recognize that this is indeed a potential created by a multipole sitting at Rj. So physically, you have now densities that live on these spheres here, and the somehow electrostatic potential, if you want to think like this, that these densities are creating is equivalent to multipoles that sit here in the centers. Okay, so if you know the fast multipole, then you know that usually it only takes into account point charges and not multipoles. So we adapted a FMM library, ScalFM, to also deal with multipoles that are input. So the first step of a FMM is indeed taking all the point charges and write one representative multipole in the center of the box at the lowest level of your octree that generates the same potential outside of this box. And instead to have so-called P to M operator, you need now to have M to M operator. But these are some technical details. Okay, but the message here is you can derive a numerical method that scales linearly with the number of inclusions. So this is a deterministic scalar case. So we put the spheres on C3, and each of them has a radius of 0.25. The contrast is 10. So this is for the first definition, and these are for definition 2 and 3 that I here repeated for sake of simplicity. So we did a reference benchmark with finite element computation, since this is a periodic case. So we have different discretization levels for the finite element, and then from these three we extrapolated, because it was already taking a long time to get this, and we saw that we are far from convergence if you look here. So we extrapolated and got this guess of extrapolated. Now, on the other hand, we did the numerical method that or this whole framework that I just presented for different kind of discretization. So n is the maximum degree of spherical harmonics here. So n equals 1 means actually only 4 degrees of freedom per sphere. So you have some kind of a dipole approximation of your density here. Then n equals to 2 means 9 degrees of freedom, and n equals to 4 means 16 degrees of freedom per sphere. And what you see is actually that you don't need that go high in discretization in terms of spherical harmonics, since the error due to the truncation of R is dominating. Here all these curves lie almost on top of each other. And yeah, so we see that definition 2 and 3 seems to be better, less oscillating as R tends to infinity. This is a general statement that can be made. Now, what about convergence rates? So I computed some kind, what I call exact solution with almost 280,000 spheres. And to give you an idea on computing time, this took like 2 hours on this laptop. Then I traced the error in the energy, and while with some good hope you see some like 1 over R convergence, so this is 1 over X for A1, and 1 over R to the power 1.5, this is this line that can be compared. Now, there is, I should mention that we need to solve an optimization problem, right? Because we had a concave energy functional where we look for the coefficient, and you can use a Amicho algorithm, since this whole methodology allows also to compute derivatives with respect to the actual homogenization coefficient. So you know what is the gradient. So you have access to the energy function plus the gradient, so you can have a good optimization procedure. Now, since here the maximum and the minimum are diverging, this tells you something. This tells you somehow that the average is converging faster. So if now, instead of just evaluating for certain r's, you say, I do an integral or average from, let's say, r to r plus 1, then you get better approximation errors. Of course, there's more computational work because you have this integral that goes maybe from 10 to 11 to get the data point at 10, and from 11 to 12 to get the data point at 11, and so on. But you see here, well, it's not a clean curve, I have to admit, but that this is decaying faster. And here I have no explanation why this kink happens somehow. Maybe there's numerical noise that comes into play. Okay, but this is purely speculative. But this is just to say that instead of having a single R, you could also think that you take some width of R that has maybe length 1, and you do an average of from R to R plus 1, some windowing. Okay, a second test case. So we have some spheres that are randomly located. However, there's a minimal distance between them of 0.4. The contrast is uniformly distributed between 20 and 50. The radii are also uniformly distributed between 0.1 and 0.25. So these are like 32,000 spheres in the largest configuration when R is equal to 20. And so here we illustrate the three definitions of the homogenized material coefficient like this. And we see again that A1 is oscillating more strongly than A2 and R3. And we have linear computation time. These peaks here are due to some additional, at some point the optimization algorithm decides to do one more iteration, and then you have a high peak here and so on. But if you go on, this is a linear curve. Okay, so if time permitting, 2 minutes. Yeah, okay. Yeah, I'm going to be fast. But this is related to a completely different but very interesting physical problem. That is, if you have charged dielectric spheres, you take two charged dielectric spheres, they have both positive charge. You might find configuration where they are attractive. Although the net charge of each of them is positive. So you see here's the energy. So this is the zero, they are infinitely away. Then you bring them together and they can polarize each other. And after some energy barrier, you might have an energy level that is lower than being separated completely, although the net charge of both of them is positive. And as you could have guessed, the equations are almost the same than in the stochastic homogenization. And you can try to explain some aerosol growth in the atmosphere of Titan if you're interested. But this is nicer movie here, where you can do dynamics of charged spheres, dielectric spheres, where they can attract and repel each other and so on, which brings me to the conclusion. So here we introduced a new embedded corrector problem that was a definition somehow motivated by a numerical roadmap. But we did not say we truncate the domain. We said we still have an unbounded domain, but I truncate my data and I complement it by a constant field on the outside. So this leads to new definition of effective matrices that are proven to converge to the homogenized one. One key point is to cast this as an integral equation that you can efficiently discretize with spherical harmonics, and the fast multipole method in order to have a linear scaling with the number of inclusions, which allows you to go to a large number of spheres even on a moderate 4-year-old laptop. So this is the literature, and thank you for your attention.
Can you say something about what will be the computational gain by putting this effective medium around? I mean, if you just took and made it the main bigger and bigger, it's from the computational point of view.
To compare it with a standard method? Yeah. This still needs to be done. Okay. But we are quite flexible. If you restrict yourself to spheres, we can have any kind of radii or contrast and so on, as long as there are sharp contrasts. So, yeah.
All your pictures, your sphere never intersected.
Yes.
Also used in practice.
So in practice, for the integral equation, we do have a problem if we have something like this. What we do is this is a practical trick, and this somehow is also responsible of this large fluctuation, is that we compute the volume that is not respected if we neglect this sphere, and we inflate those so to have the correct volumic fraction of the inclusions.
I don't know what it means for your integral formulation, but if you did that using usual boundary conditions, you would introduce a boundary layer effect again. Because in fact, I mean, there's no chance that your big sphere wouldn't intersect something. So you're changing the laws of the point.
Yes, I mean here you would have material A0, here some AI, and here, let's say, A infinity. And well, the methodology heavily relies on the fact that this is the spheres. When you have now to do a detour like this, you can do it by domain decomposition approach, iterating between those two, but then you need a very high degree of spherical harmonics for this one. We tested it, it's not worth the effort. So we decided to cancel those and just make them bigger.
All right, I would suggest to postpone further discussion and continue with next talk. And thank you once again.